Hello, 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 and good morning. We can only barely just say that. Whoa, cancel. Um, Good morning. Good exams eve. Um, I hope your weekend was all sunshine and rainbows. It was kind of drizzly for me, but I still got to get out on the board a little bit and ride around, which was nice. Hey, Winnie, how you doing? It has been a busy weekend. For me, the department is currently it's hard to talk and type at the same time. The department is currently getting geared up to publish the summer schedule. Hey, Raj, and and so there's been a lot of a flurry of email communication surrounding that. Oh, hang on. We're getting. I always forget. I have concurrent with the stream. I have the video live streaming through the computer just so I can get a sense of where the lag is, like where I say or write something versus when it actually shows up on YouTube. But every morning when I do that, I forget to mute my speaker. So there's always this one moment where I hear my voice coming back at me, but it's something that I said a couple seconds ago. So did class schedules get delayed? I'm not exactly sure, but here, let me pop open my email really quick. We got one that told us when the summer schedules will be published. Let me pop this open. It's on track to be publicly released April 13th. So what are we looking at? Today's the 30th. So it looks like 2 weeks from today. Summer schedule should be up. Let me just add this to the comments. Again, everybody's kind of scrambling to get all of our classes online, and because summer is going to be completely electronic, and so there's having to be a little bit of we're never gonna meet again, right? Oh my goodness, that sounds so final. We're definitely not gonna meet in our classroom, that's for sure. Hopefully we'll meet again sometime in this life. You'll know where to find me online because I'll continue using this channel. Are you giving a class in the summer? I am. This summer. Wait, are all summer classes going to be online? Yes, they will. All summer classes will be online, and it's uncertain what fall will look like. Don't get too sad. Why does it say Chem 400 office hours? Probably because I mistitled the thing. Here. At least I got the date right. Chem 400. This is not an office hour. This is lecture time. Let's save that business. All right, now hopefully I don't know how quickly that turns around. I just edited the title to say Chem 400 office hour. I wonder if it'll change if I refresh the page. Oh, yep. Now it says lecture instead of office hour. If you hit refresh on your page. Yeah, no, this is not an office hour. This is totally normal lecture. And we'll get into it in just a bit. yeah, this is totally lecture. We're going to cover some new material, and then after we get through talking about some electron configurations this morning, I can field more questions about the exam. The exam has soaked up pretty much my entire weekend. It's almost done, which is good because it's going live tomorrow, right? Some people have already sent in homeworks 5 and 6. You totally can at any moment. I'm taking them now, but they're due the day of the exam. So cutoff is 11:59 p.m. tomorrow. But if you have it done, you can send me a picture, a PDF, a Word document of the homework answers, and I'll take that at any time. I'll be able to answer some questions about the exam a little more intelligently because it's closer to being done. Holy moly, I you know that feeling you get when you're crunched because it's like finals and you've got a deadline? That's the feeling that I'm getting writing this test because it's got to go live tomorrow. I literally did nothing. I sat at a computer from about 10 o'clock in the morning yesterday till 1 p.m. And just worked on it. I wasn't starting from scratch either. I had been working on it the entire time, and I'm barely beginning to see the light at the end of the tunnel. So it'll be ready for you guys, and it'll be going live tomorrow. And again, we'll talk a little bit more about that after class. Our song of the day. Our song of the day is Losing Friends. Oh, that sounds like we have a runaway baby in the other room. Losing Friends by Death from Above. Death from Above, 1979. Great band, two humans. Weird, like danceable hardcore punk with no guitars. And it sounds like a contradiction. Punk needs a guitar, right? Well, this band doesn't use one. There is a bass guitar, but no proper guitar. Check them out. The link is in the description. Hopefully, we're not losing too many friends, and maybe we're even making some. Interacting with humans we may not necessarily interact with in this online electronic ocean. Okay, I think I've killed enough time. Let's go ahead and dive into some new content. Again, today's lecture, by way of reminder, there's my kid. Today's lecture is Exam 3 material. So if you're here, I'm glad you're here to hang out live with me, so I don't feel so lonely. But if you're not here, my guess is that you'll probably be coming back. Sorry, and I just adjust my microphone a little bit. Come back later to watch it after Exam 2 is gone. Heck yeah. Jesse knows what's up. Great band. Check him out. Awesome studying music if you need something that's a little on the intense side. All right. Enough is enough. Let's actually dive into new material, because once we get through today's lecture material, we'll be able to I'll be able to take more questions about the test. Okay, so up to this moment in time, we have been looking at the electronic structure of an atom, right? We've been zeroed in, focused on specific electrons, and we've been describing electrons through their wave function. Oh, hang on. There we go. So, individual electrons are defined by their quantum numbers, right? By N, L, M sub L, and M sub S. And we concluded that discussion last lecture. All right. And so individual electrons are defined by their quantum numbers, and we've been kind of focused in on individual electron particles. What shell are they in? What subshell do they belong to? What specific orbital are they in? What spin do they have? And those are our 4 quantities right here. And again, you can reference last lecture to get a refresher on what those mean. Now, we're going to do a shift today. We're going to start a discussion. We're going to start looking at the electronic structure of an atom. All right, the electronic structure of atoms. Rather than looking at individual electrons orbiting an atom, we're going to look at all the electrons orbiting an atom simultaneously. All right, and we're going to learn two ways to describe the electronic structure of an atom. The first is called an electron configuration. And the second is called an orbital diagram. So we have electron configurations and orbital diagrams. All right, these are the 2 things we're going to be learning what they mean, how to write them today. And one comes from the other. Once you write the electron configuration, the orbital diagram is just a different way, of communicating the same information. Now, before we dive in, there's a couple things that you want to keep in mind. There's a few things you need to know before you can start writing electron configurations. The first thing to remember is, as we go about doing this, you want to remember first that lower energy orbitals fill first. All right, so when we are placing electrons in orbitals, we always fill the lowest energy orbitals first, right? Because the electrons want to get as close to the nucleus as possible, so they're all going to crowd around the low ones and then fill out ones that are a little farther away and then farther away. So we'll first fill our first shell, second shell, third shell, etc. The second thing you need to keep in mind is something called the Pauli exclusion principle. The Pauli exclusion principle, which tells us that one orbital holds a maximum of 2 electrons. All right, one orbital holds a maximum of 2 electrons. So 2 electrons fit in an orbital, then we fill, then we move on, etc. The third and final principle you need to keep in mind to write electron configurations is something called Hund's rule. All right, and Hund's rule, I'm gonna give a very blue collar definition of Hund's rule. All right, so if you look it up in the book, it'll say something else, but this always helped it stick in my memory. Hund's rule says that electrons are children period. In other words, they only share a room if they have to. All right. Electrons are children. They only share a room if they have to. Okay, with these 3 principles in mind, we can start writing out electron configurations. All right, and there's one there's one last thing that I want to mention because I believe that not I believe I know you'll find this useful. This is something that is probably in your notes from last week. I just want to rewrite it here because you'll want to have this at the ready as you go as you go through the next few examples that we're going to work together. So you'll remember this graph where we have energy on the y-axis, and in the first shell, so for n equals 1, there is one solitary s orbital. On the second shell, when n equals 2, there are two subshells. The s, which has 1 orbital, and the p subshell, which has 3 orbitals. On the third shell, we now have 3 possible subshells: the s with its 1 orbital, the p subshell with its 3 orbitals, and the d subshell with its 5. And then finally, on the 4th energy level and every energy level above the 4th energy level, we have, whoa, let's undo that. There we go. On the 4th energy level, we have the S subshell, the P subshell, the D subshell, and the F subshell. All right, and keeping this thing, you want to keep this at the ready because it'll definitely come in handy as we move to start writing electron configurations. Right now, with these 3 principles in mind, and this little graph showing how the subshells, which subshells are available on which shell levels, let's start writing electron configurations. So all right, and we're going to start with the hydrogen atom. All right, now when you look at hydrogen on the periodic table, hydrogen has 1 electron, right? 1 single electron. Yep, that is totally correct. That is correct, Salvesh. The number of orbitals available in each subshell increases by odd numbers. It starts with 1s, then 3p, 5d, 7f. Always hitting those odd numbers. Now, a hydrogen atom has 1 electron, all right? And we know, excuse me, I just bopped my microphone. We know that hydrogen will want, that 1 electron will want to be in the lowest energy orbital possible. So we're going to first look to our first shell, right, where we have 1 s orbital on the first shell. So this electron wants to be in the 1s orbital. The way you write the electron configuration for this is like so. Oh, goodness. Some days Photoshop is awesome, some days it's a little finicky. The electron configuration for hydrogen will look like this, 1s1. Okay, now here's kind of a key to what all these pieces mean. First off, this coefficient out in front, this is the shell that you're in, all right? This is N. All right, it is our shell. As I'm sure you can guess, this S right here is determined by our value for L, all right, the angular momentum quantum number, and this tells us the subshell. All right, and then finally, this superscript right here, this 1, tells us this is the number of electrons. The number of electrons, I should say, here actually, the total number of electrons housed in that subshell. All right. Sorry, Braj, I'm just now seeing your question. Does n equal the number of outcomes? No. N equals the principal quantum number. I.e. the shell. The energy shell. Okay. So, yeah, n is the principal quantum number, or the energy shell. All right, so that is what each component of the electron configuration means. So when you write the electron configuration for hydrogen, you would write it as 1s1. All right. Now, when you look, let's do the next one. All right, here we got helium. All right, now helium has 2 electrons. All right, we know that the first electron that helium has is going to go into the 1s orbital. All right, and this is where the Pauli exclusion principle comes into play. The second electron that helium has also is going to be housed in the 1s orbital, because we know that every orbital can house a maximum of 2 electrons. All right, so helium would have the electron configuration 1s2. Okay. Now let's do lithium, which is the third element on the periodic table. All right, so one more electron than helium. We know that our first 2 electrons will go into the 1s orbital. All right, but helium has a third electron to place. All right, helium has a third electron to place, and we know from the Pauli exclusion principle that there is no more room in our 1s orbital because each orbital holds a maximum of 2 electrons. So the third electron for lithium needs to go. We know that our first shell is completely full, so we have to move up to the second shell for lithium. Now, on the second shell, we have 2 subshells. There's the S subshell and we have the P subshell. For the first time, we actually have a choice between which orbital gets filled. On the first energy level, there's only the S orbital, but now that we have a third electron that will be housed on the second shell, we have a choice. Does it land in the 1s, sorry, not the 1s, in the 2s or 2p subshell? And we know that an electron will always select the lowest energy possible, so that third electron from lithium will select the s orbital, because we know that s orbitals are lower in energy than p. So the electron configuration for lithium will be 1s2, 2s1. All right, and that is the electron configuration for lithium. All right, any questions so far? Are we good? Gonna wait just a minute for the video to catch up. While I do, I'm actually gonna draw that little graph over here because I think it'll be useful to have. n equals 3, we got 1s, 3p, and 5d. And then n equals 4. There's 1s, 3p, 5d. Let's see, I gotta lasso this over. And 7. Whoa. There we go. And 7f. Okay. Let's see. Unable to connect. Oh, we're disconnected. Let me check my stream health. Wi-Fi connection strong. Okay, hang on. Okay. Sorry, we're having a little bit of a technical difficulty. Give me 1 sec here. Okay, sorry, I was having a couple technical difficulties. But I'm trying something here. Hopefully, let's see. Give me one moment. All right, it's a couple technical difficulties. But I'm trying something here. Hopefully, let's see. Give me one. Okay, I'm almost back. Almost back. Okay. 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 Oh, an error occurred. Okay. I apologize for that lag. Getting back to it now. I just have to pull up my lecture notes. Okay. Okay. All right. Apologies. We're back on track. So we wrote out the electron configurations for lithium. Let's go ahead and write out the electron configuration for boron. All right, so boron has 4 electrons, and we know that the first 2 electrons for boron are going to go into the the 1s orbital, and that the next 2 electrons will go to the second energy level. All right, and And they will, again, electrons want to get into the lowest energy orbital possible. And so they're going to select the 2s orbital because the s orbital is lower in energy than the p. And they want to be as low in energy as possible. All right. Now, when we move from boron to, wait, did I do that right? No, sorry. Boron has, 5 electrons, right? Sorry, beryllium has 4. Be is 4. Boron has 5. So it's going to have all the electrons that lithium has, 1s2, 2s2, and then it'll move to, now that the 2s subshell is full, we're going to place our first electron in a p orbital. All right. Yeah, totally. So that is correct, Jesse. Boron does have 5. All right, Diana, question. Oh yeah, sorry for the sorry, I'm just catching up on everybody's questions. My Wi-Fi was disconnecting. The wallpaper though? See, Diana, so every subshell slot can hold 2 electrons. Yes, Diana, that is exactly correct. Because every orbital can hold 2, since the p subshell has 3 orbitals in it, it can hold a maximum of 6, and we'll see that in just 1 second. Sorry, yeah, my Wi-Fi is giving me some trouble. Oh. Here, hang on 1 second. Alrighty. Okay. I am sorry. This morning is just riddled with technical difficulties. Okay. Oh wait. I may have one last recourse. Sorry. This is me kind of doing stuff on the fly. All right. Sorry. I apologize for how faltering this lecture's been. Let's see. Okay. But now I think okay. Sorry. Since the corona started, Salvesh, you're feeling my pain then. My Wi-Fi is usually pretty solid, though we had a problem with it last time. This time it's being really, really, really lame. I'm actually, hang on. I think I got things figured out, but I just want to just switch one more thing. Fortunately, the Surface platform is still working, but everything else seemed to have died. And I normally manage the comments on a second screen. That has died. But I'm trying to boot up. Okay, here we go. Here we go. Okay. Oh, wait, no. Go back. Sorry. Hang on. Thought I had this locked and loaded, but apparently not. Let's do that. Oh my gosh. Wait, let's do that. Now let's do this. Holy moly. Okay, sorry, last login. All right, don't stop me now. Awesome. It actually worked. Okay, here we go. We should be back in business as of right now. Okay. Restart the okay, thank you all for your super helpful input. We should be good now. I think we'll be good to roll without restarting the router, but I am going to give the situation a little bit of tender loving care after our stream concludes. I apologize. It's taking it's been so faltering this morning. Thank you all for your patience. Okay. So we've managed to do 5 electron configurations. Let's let's bust out a few more. Let's do carbon. Let's do carbon. Let's do nitrogen. And do oxygen. Excuse me. Okay. So, carbon. 6 total electrons. We know our first 2 will fill up our first shell with a 1s2. Our next 2, so we've got 4 left, will be housed in our 2s orbital, and our final 2 will get housed in our 2p subshell. All right, so that's carbon. Nitrogen has 7. So 1s2, 2s2. Now we have 3 electrons left to place, and we're going to put them all in the p subshell. Remember that this number right here, that is not the number of electrons in an orbital. This is the total number of electrons in the subshell. All right, total number of electrons in the subshell. And since there are 3 p orbitals, that means that the p subshell, as Diana already pointed out, can hold 6 electrons total, all right? So don't trip if this superscript exceeds the 2, because that is representing the electrons in the subshell, not the electrons in the orbital. All right. Now, moving down to oxygen, this will be 1s2. We've got, 8 electrons to place. 2s2 and then 2p4. All right. So hopefully these electron configurations are starting to feel a little fluid. It would be my pleasure to. Salvesh is just just said, because of all the technical difficulties, I owe you 30 more minutes of instruction. It would be my pleasure. I actually really, really enjoy live streaming. I obviously miss seeing everyone's faces. It's weird cracking jokes into a microphone because there's no either laughter or groans because my jokes tend to be terrible chemistry dad jokes. But I don't know. I'm having a lot of fun with this format, doing something new, interacting with you all. So yeah. I'm totally down to hang out longer. Now that we have a more stable situation. All right. So, all right. Now, hopefully, our electron configurations are feeling more comfortable. Here we go. All right, and these are electron configurations. I want to take a moment to introduce orbital diagrams. Oh, hang on. That lovely little musical interlude is one of my kids' iPads making a lovely little chime. Okay. All right. So we've talked about electron configurations. The orbital diagram, you write an orbital diagram based on the electron configurations. All right. Now, the way the orbital diagram communicates similar information, just in a different format. All right. In an orbital diagram, each orbital is represented by a line. So, for example, for beryllium, we would draw one line for the 1s subshell, a second line for the 2s subshell. And each subshell you label, not just the subshell, but the shell also that they belong to. I'm actually going to give myself just a little more room to work with. I'm going to do some lasso tool rearranging here. This is a luxury we could never enjoy on a whiteboard without erasing and redrawing. It's kind of fun to do on the digital slate. All right. Okay, so alrighty. So with beryllium, because we have 2 electrons in our 1s orbital, we're going to, the electrons are represented as arrows, all right? In the first one, we go like this. The second one, you place in the 1s orbital, right? So there's 2 electrons there. And you'll notice that one arrow is pointing up and one arrow is pointing down. The arrow orientation represents spin. So this is m sub s is plus 1/2, and this represents an m sub s that is minus 1/2. We know that the spin quantum number for 2 electrons in the same orbital can't be the same, and there are 2 allowed values, positive and negative 1/2, and that is represented by the orientation in which you draw the arrow, okay? So you can never draw 2 arrows both up or both down if they are in the same orbital, all right? So that is the electrons in the first orbital. The second orbital, the 2s orbital, we have one up and one down. Jake, you wish you had a lasso tool to move your notes when you write in pen. Dude, that's why tablets are where it's at. Yeah, totally. It's the lasso tool is revolutionary when it comes to reorganizing notes, and if you're working digital, you can enjoy it in your notes as well. Alrighty, so this is the orbital diagram for beryllium. You can see how the orbitals are represented by lines, the electrons in the orbitals are represented by arrows, and we have to keep in mind the orientation, the spin of said orbitals, either up or down. So with this knowledge, let's write the electron configuration for boron. So here we have 3 subshells in play, the 1s, the 2s, and the 2p. All right. Now you'll notice that I'm writing, since we're dealing with the 2p subshell, I write in all the available orbitals in that subshell, even though, as we'll see, we're not going to fill them with this, with the electrons in this atom. So we have 2 electrons in our 1s orbital, 2 electrons in our 2s subshell, and only 1 electron in our 2p subshell. It does not matter where you put this 1 electron, because all the p orbitals, all orbitals in the same subshell, that I go talking like Sean Connery again. All orbitals in the same subshell have the same energy. All right, all orbitals in the same subshell have the same energy. Vraj, what about parallel spins? We will see that in the next example. All right, so with carbon, all right, this is where we have, for a parallel spin, will the spins ever be both up or both down? Okay, Diana and Raj, I'll answer both of those questions with our next example. When we look at carbon, we have the 1s subshell, 2s subshell, and 2p subshell. All right, now, we already know how the first 2 orbitals are going to go. 2 electrons in the 1s, 2 electrons in the 2s. ESP is real. Now we have 2 electrons to place, and there are 2 correct ways to write this in. You could, whoa. So this is where Hund's rule comes into play. You'll remember that I said that electrons are just like children. They only share a room if they have to, right? That's because, given the choice, electrons will never share an orbital, because they had to share orbitals when it came to the 1s and the 2s, because that was the lowest energy orbital available. However, with the 2p orbitals in the 2p subshell, we have 3 orbitals all with equal energy. So the 2 electrons housed in carbon's 2p subshell won't go to the same orbital because electrons repel each other. They'll spread out. They each want their own room as long as they can. So this is one correct way to write the electron configuration for carbon. But there's a second correct way. You could write it like this, or you could also write it like this. With your 2p subshell, you could put 1 electron you could put your 2 electrons in different p orbitals and have them both pointing down. All right? So those are 2 correct ways to write this. There are also 2 incorrect ways. So you could do it like this or like this, but not like this. There are 2 wrong ways to write this in. Not like this or this. All right. What are the 2 wrong ways to do it? First, it'd be wrong to place both electrons in the same orbital because, as we said with Hund's rule, electrons would rather not share an orbital if they don't have to. So it's lower in energy to have those two electrons in separate orbitals. All right? So that's one wrong way to do this. The second incorrect way to do this would be to have one electron spin up and one electron spin down. All right? And here's the reason why this is incorrect. All right, so this... actually want my box to be more like this. This is also incorrect. And here's why. The spin, m sub s, represents a magnetic field. All right, the individual magnetic field created by each electron. And magnetic fields, these magnetic fields want to be aligned. All right, these magnetic fields want to be aligned. And so you'll never have electrons in a single... you'll never have electrons in two orbitals with anti-spins. The spins will always be parallel because they want to align their magnetic fields together. Just like magnets snap to have their magnetic fields line up, electrons will as well. So you can draw them as both pointing up, or if you're into Soundgarden and you want to go down on the upside, you could have them both pointing down. But what they'll never do is have one up and one down, because the magnetic field of each electron will attract the other and it'll snap to be the same. Yeah, totally. So we always want either both up, both down, but if they're in different orbitals, the spins must be parallel. They can't be separate like that. Hopefully that answers Raj and Diana, both of your questions. All right, so know that when I draw the electron configuration like for carbon like this, all right, whoops, like this, you could draw them both down. You could draw them in different orbitals than I have, as long as the one thing you have to do to make sure that your answer is correct is your spins must be parallel. All right, Salvesh. Are there any equations applied to orbital diagrams? If so, will the two electrons spinning up have different answers from the ones spinning down? Okay, so this portion of the class, we're not really looking at, we're not doing a lot of math other than counting electrons, seeing which electrons land in which orbitals. So we will not be doing any like calculations with this stuff per se. The one thing that it would affect is if we were assigning quantum numbers, wave numbers for these electrons. If they're all spin up, they would all be ms equals plus 1/2. If they were spin down, they'd be ms equals minus 1/2. And that's how they would differ from... that's how those answers would differ from each other, but they would all be equally valid because they'd all have the same energy, if that makes sense. So do the same equations for the electron configurations work for orbital diagrams? Yes, and in fact, they share similar... So Raj, great question. They share similar information, but you'll notice that in the orbital diagram, there's a little bit more information. The orbital diagram actually tells you something about the spin state, whether spins are parallel or not, whereas the electron configuration doesn't explicitly state that information. So if you look at the 2p for carbon, in the electron configuration, it's just 2p2. But in the orbital diagram, you can see that you're actually dealing with parallel spins. Totally. You're absolutely welcome, Salvesh. Okay. So, that is the electron configuration for carbon. Let's go ahead and write out the electron configuration for nitrogen. So we have 1s subshell, the 2s subshell, and the 2p subshell. All right, and we've got 2 electrons in our 1s, 2 electrons in our 2s, and now 3 electrons. 1, 2, 3. And because nitrogen has, sorry, not nitrogen, because the 2p subshell has 3 available orbitals, each electron gets its own room. They're a happy kids. All right, now let's take a look at oxygen. All right, so we have sorry, 8 electrons. If you can hear what sounds like laughter and happy sounds coming from the other room, it's because I have like a 1.5-year-old, and my 2 brothers are over right now. So he's got both uncles laughing at everything he does. They think he poops gold. That's mostly because they haven't changed his diapers yet. But it's pretty cute. Okay, that helps with paramagnetic and diamagnetic theory. Yes, so diamagnetic is when 2 electrons, a diamagnetic compound is a compound where all of the electrons are paired. All right, so you don't have any buildup of a magnetic field, whereas a paramagnetic compound is one where you've got a bunch of electrons with parallel spins, and we'll see examples of that probably not today, but in a future lecture, Wednesday's lecture. All right, so let's go ahead and write the electron configuration here for oxygen. We've got 2 electrons in our 1s orbital, 2 electrons in our 2s orbital, and now we have to place 4. So we're going to start by placing as many unpaired electrons as possible. 1, 2, 3, but we have a 4th one. So somebody's got to share a room. All right, someone has to take that 4th electron. Doesn't matter which orbital you put it in, but you have to put that 4th electron spin down in a p orbital. All right, and this is what happens when a family starts having too many kids. So, for example, when I was growing up, there was there were 2 kid bedrooms. All right, and it was fine because it was me and my sister, and I was 5 and she was 3, and we each had our own room. But then my parents had another baby, and it was a baby boy. So I went from being an unpaired electron in an orbital all by myself to now there was another electron sharing my room with me. And that is the essence of Hund's rule. There's only so many rooms in this house, and the electrons got to go somewhere. So you end up sharing a room with your little brother electron. And that is what's going on right in here. All right, cool. Okay, so this is our, this is the baby brother. Baby brother electron. All right. So that is our intro to electron configurations. Let's get ready to take the next step. Let's see, where are we? We've been streaming for about an hour. Okay. So, I want to do 2 more electron configurations. Let's take a look at neon. All right. Neon has 10 electrons. Our first 2 electrons will go into our 1s orbital. Oh, let's see. Raj, you got a question. What can the possible states other than half-filled and fully filled? What can the possible states maybe be other than half-filled and fully filled? Well, it honestly depends upon the number of electrons that you're dealing with. There's all manner of states that can exist in between fully filled and partial and half-filled. So half-filled tend to be the paramagnetic compounds, because when you have a half-filled D subshell, and we'll see what that looks like in a bit, that's what leads to strong magnetic behavior. And then there's the diamagnetic where and you'll notice by writing out these electrons, actually electron configurations, very few of them have every electron spin paired. as individual atoms. But that's usually why these atoms form molecules, and in molecular structures, every electron is paired, and we'll see how that happens and why that happens when we get to Lewis structures. So some of the answer coming this lecture or next lecture, and then more answers ahead. Hopefully that's not too. I'm not abdicating my answer too awfully bad. All right, let's write this electron configuration for neon. Now, our first two go into our 1s subshell. Our next two go into our 2s subshell. We have 6 more electrons to place, and fortunately, we have 3 orbitals in our 2p subshell. So all 6 of our remaining electrons can go into the 2p, and this is the electron configuration for neon. Next, I want to write the electron configuration for sodium. Now, sodium has 11 electrons, which means it has just 1 more electron than neon, right? So sodium, because we just wrote the electron configuration for neon, we don't need to think about where to place the first 10 electrons. We know it's going to be exactly the same, and now we need to place that 11th. And you'll notice that our 2s and 2p subshells are totally full, so the 11th electron for sodium has to go into the third subshell. Sorry, not the third subshell, the third shell. On the third shell, there's the 1s, the 3s, 3p, and 3d subshells. Given a choice, our electron is going to go into the s orbital because the s orbital is lower energy than p. P is lower energy than d. So our final electron will be 3s1. All right. Now, I want you to notice something. You'll notice that sodium has all the electrons that neon has plus 1 more, right? It's almost like there's an entire neon atom housed inside sodium. That sodium has this neon inside it, plus it has this extra electron out the other end, all right? And I'm sure you can see that these electron configurations have the potential of getting very long, all right? They have the potential of, getting very lengthy because atoms have a lot of electrons, right? Here we are. We just wrote out the electron configuration for the 11th atom on the periodic table. We're going to get into the hundreds by the time we're done, all right? And without a system of abbreviation, these electron configurations will get unwieldy to write. However, we do have, chemists have developed a system for abbreviating electron configurations using the noble gases, of which neon is one. So this is called, right here, the full electron configuration. Oops, not fell. Full electron configuration. All right. And it's wonderful. There's nothing wrong with writing the full electron configuration, but we can use something called the Nobel gas abbreviation. Nobel gas abbreviation. All right. And the way you use the Nobel gas abbreviation is like this. You say that sodium has all of the electrons that neon has. You find its nearest noble gas with fewer electrons on the periodic table. And you put that elemental symbol in a bracket. Sodium has all the electrons, the electron configuration that neon has. Place it in a bracket. So all of this goes here. And the remaining electrons still go on the out. Whoa, that's very bright. Go on the outside. So you throw a neon in bracket and then 3s1 and this. So that you still write. This is called the Nobel gas abbreviation. It is far more concise in a more compact way than writing the full electron configuration. On the exam, so when I test for this on exam 3, I'll never ask you to write the full electron configuration. You're always welcome to use the Nobel gas abbreviation just because it's much more user friendly. Alrighty. These electrons that are on the outside of the bracket have a name. All right. These electrons out here are known as the valence electrons. All right. They're the valence electrons. In other words, they are the electrons in the highest energy orbitals. And we will be doing a lot more with valence electrons as we move into the future. All right, any questions so far? It's been a kind of a haltering kind of first lecture. Hopefully it's been mostly a review. I think this is where I want to pause. We will definitely continue with our discussion of electron configurations on Wednesday. But we have this giant thing standing in between us now and our future 48-hour selves. And that is exam 2. Okay, sorry, we do have some questions rolling in. Are they the ones called active, used for bonds? Yes. Yes, the valence electrons. Electrons are the ones used for bonding. So that is absolutely the case for Raj. The valence electrons are the ones that are used for bonding, both forming ionic bonds, as we'll see in a bit, and covalent bonds. But that's a little bit ahead. That's maybe a few lectures out. Totally. So, other questions about what we've covered so far? Okay, let's pause. New content. Where are we? There's our. And let's talk about exam 2. I know we have before, but I essentially from this moment out, I am totally down to answer questions about exam 2. I think the biggest thing that I would say is C. I would take a look at the Canvas announcement. The Canvas announcement. If you haven't already, because it has a ton of detail, all of the technical information. You may, if you've seen the Canvas announcement, you'll notice that the multiple choice, the Canvas multiple choice time got extended, and the reason why I chose to do that for the multiple choice is I was trying to emulate the ACS final. So the multiple choice portion has 30 questions in 50 minutes. All right, and if you crunch the numbers on that, 50 divided by 30, that is 1.7 minutes per problem. And this kind of emulates the ACS final, which we won't be taking the ACS final, but on the ACS final, you have 150 minutes, not 150 minutes, 110 minutes, 1 hour, 50 minutes, to do 70 questions. So if you do 110 divided by 70, you have, on the official ACS exam, you have 1.6 minutes per problem. And so that's why I bumped the time from 40 minutes to 50 minutes to kind of approximate that testing situation that the ACS standardized exam uses. So that's the reason why I tweaked that. Let's see. No ACS. Oh, okay. There's a question. Yeah. So Raj, in the syllabus, it said that we are going to be taking the ACS standardized final exam, but that's no longer possible to do electronically because the ACS exam is a sealed exam. So what that means is there's literally no digital copies are allowed to be made. If any digital copies are made of an ACS final exam, the exam is considered compromised. So it there's like I couldn't like scan it and send it to you and have you send it back because that would be a breach. There's no way to even administer it online because if I did that, then even if it was through a timed thing through Canvas, you could still snap pictures of your screen with your phone, and that could compromise the exam. So we will be unable to do the ACS final for our final. So what are we going to do for our final? It depends. I might do a 100% Canvas exam online. I might do a mix of kind of the Canvas half and a take-home half, like we're doing here with exam 2. It's all an experiment at this point. Part of it is, it's an experiment. I've never done this before. So this exam 2 is my first data set. So we'll see how this exam goes. I'll kind of look to see, okay, how did the class do? Do they do the same on the take-home versus the multiple choice? Is there a disparity? Should we tweak for exam 3? And then based on how exam 2 and exam 3 go, I'll make a decision about the final. Okay, so let's see. So questions. So they're all piling up. So yes, Jesse, that's correct. We will not be taking the ACS final. Sarah, is this more time than you would normally give? The answer to that question, is this more time than I would normally give? I don't actually have an answer to because I never give multiple choice exams. So you took my exam 1, right, which was all long answer problems, right? They're all word problems, solve these word problems. The tests that I normally write that I give in class are all in that format. So I give 80-minute word problem exams. With multiple choice, so this is the first multiple choice exam I've ever given, and half of it will be multiple choice, half is a take-home written. And so I didn't really have any baseline to go off of for how much time should the multiple choice have. And that's why I looked to the ACS format, because that is 100% multiple choice. And so I thought, okay, if they give 1.6 minutes per problem, I want to at least give that, and I gave you guys a little more, 1.7 minutes per problem. So that's how I arrived at that number, that time. And the multiple choice questions range from very easy no calculation questions, like you just look at it and you're like, oh, yep, that's that. To there are some that have a little bit of calculation, and then some that have some moderate calculation involved. So they're not all the same. Some take more time, some take less. So I'd recommend flipping through, finding the ones that are easy, knocking those out first, and then taking more time on the ones that require more. Okay, Diana, your question: will the final be all multiple choice. I kind of answered that a little bit. I don't actually know yet. I'm going to I'm entertaining the possibility. The final may be all multiple choice, or it might not be. Part of it depends upon how exam 2 and exam 3 go. Like I said, I'll be evaluating the exam 2 process once I get the results in. That will inform my decision on what to do for exam 3, and then exam 2 and exam 3 together will inform the final form that the final exam takes. All right, Vraj, let's see. A lot of pre-meds. Oh, let's see. Whoa, where'd you go? A lot of pre-meds want students to take... A lot of pre-med med schools want the students to take ACS. Does that mean we might have to take the course again? Okay, so Vraj and Diana, same question. I'm not certain. I guess it would depend upon your specific, the specific schools you're applying to. I haven't heard of that being the case. Like of a department having a policy of you have to have taken the ACS final exam. But my guess is that if they have that policy, it was probably in place before the COVID crisis, and so I don't know how rigid they'll be moving forward. So I guess it just depends department to department. You'd have to check with them. But what I can say at this moment in time is there's no possible way to administer the ACS exam online due to the very rigid sealed guidelines that the American Chemical Society attached to it. Salvage, that is another thing. You may also take it in Chem 401. No. It's there is an ACS exam for first semester general chemistry and second semester general chemistry. So they each have an ACS final associated with it. Oh yeah, so it's technically a different test, but written by the ACS. Let's see. We might have a choice because of Corona. Salvage, I actually believe that... Well, Raj doesn't think so. I think so. Do we know? Not really. It's really up to the individual departments and how rigid they're going to be. Okay, so let's see. Retaking the course. Yeah, totally. It's honestly, it's kind of out of our hands. It kind of depends upon how this whole pandemic thing goes. Uncertain. I don't know if they're... Diana, that may be worth doing, taking a year off of school. Again, depends upon which programs you're looking to transfer to and how rigid or flexible they're willing to be. Taking a year off school can make you forget stuff, but something to keep in mind is forget stuff or waste time. Yeah, it's a catch-22. Sorry. Sarah, I will get to your question in one sec. One last thing I'll say, Raj, Salvesh, and Diana, as you ponder these conundrums, all of my classes will be streaming to YouTube, even after the pandemic subsides and things get back to normal. We're going back to hanging out in class, doing lecture. I've actually been really enjoying this format, and it's a good tool to help students you can go back and watch the videos. You can use them as a study tool. And so my plan, even when physical normal classes resume, is I'm going to continue streaming my classes online. And instead of writing on the whiteboard, I'll be bringing my Surface into class, hooking it up to the projector. So in class, it'll be a similar experience where I'm still writing up on the whiteboard, but I will also be bringing in my microphone and live streaming to YouTube as I lecture. So this resource will continue to be available both for students who are taking the class, but it'll also just be on YouTube for anybody who wants to watch or review, etc. So these resources will continue to be available from me. Okay, Sarah, yes, I am totally taking content questions for exam 2 right now. Sorry, I just now got down the... Just got down the comment feed to see yours right now. I'm totally taking content questions for exam 2. Salvesh believes... Okay, Sarah, do we need to understand how you derive an equation by multiplying constants? Or do you just need to know the equations? Right. So there are no explicit questions dealing with that kind of, this is proportional to this, let's multiply by a constant, turn it into an equal sign. That's more to give the class an understanding of where do these equations come from. Well, we have these two quantities that are proportional, but they have different units. They're measuring different things. How do we get a mathematical equation that makes them equal? So it's to understand where they came from, but there aren't any problems about those derivations explicitly. Totally. Diana, actually, like this form. Yeah. Aw. That was so sweet. As you can tell, I have a hard time talking and typing at the same time. Yeah. So yeah, I've been liking the format as well. I'm always eager to hear how you guys have been experiencing it though, because it's a different level of interacting with the material when you're trying to use it as opposed to communicate it. And I'm very interested in understanding how effective this has been in communicating. Okay, Sarah, question. Do we need to know how to recognize a reaction like an acid-base neutralization reaction, etc.? Okay, that is a good question because we didn't finish covering acid-base stuff completely before exam 1. And fortunately, there's a lot of interesting ways acid-base can fit into exam 2 with acid-base can connect to thermochemistry, acid-base can connect to gas laws. You'll recall there are gas evolving reactions. One thing that I did say when we were going through acid-base reactions is that you do need to know, the one reaction that you need to know is the acid-base neutralization. That was the one type of acid-base reaction that I said would not, I would not give you the products for. So, for example, I could write a problem that starts like this. I could say phosphoric acid reacts with sodium hydroxide running out of room. Sorry, that's just so ugly. I'm going to rewrite it. Reacts with sodium hydroxide. Boop, boop. And I could ask you in part A of this problem to balance it without giving you any additional information. All right. I could ask you to balance it without giving any additional information. Now, what that means is, what that means is it would be up to you not only to identify, oh, phosphoric acid is going to be H3PO4, right? Because it's based off of phosphate, PO4 with a -3 charge. It reacts with sodium hydroxide, which is NaOH, also aqueous because sodium is always soluble. And it produces two things. It produces water, which is H2O, and a liquid, plus a salt. And that salt is comprised of the metal from your metal hydroxide and the anion your acid is based on. So this would be plus Na3PO4, and it would be aqueous because sodium is always aqueous. And then you have to go balance it. All right. So Sarah, the answer to your question is I could totally work acid-base neutralizations into this because that is the one type of reaction I said I would not give you the products for. So you are on the hook for knowing that. That could totally show up on the exam. How to write one of these from scratch and all the components. No, I'll totally give you something to go on. At least your reactants, usually reactants and products. Oh, you guys, please teach OChem lecture and lab. Spring 2021. I would love to. I would do so at the drop of a hat. At this moment in time, I am an adjunct, which means that I gladly accept whatever teaching assignments the department gives me. So the full-time faculty kind of get first dibs on the fun classes, which are the more advanced ones. So, for example, 420, 421, 401 usually are taught by full-time faculty because, again, they're full-time. They get to write the schedule, and those classes are really, really fun to teach. But if the department ever needed me to teach organic chemistry, I would do so in a heartbeat because that class is the most fun I've ever had taking or teaching in my life. All right. Similar question to Sarah. How does equivalent weight connect with normality and molarity? Oh, and okay, so Sarah, will I tell you it's a neutralization reaction? No, I'll just say that phosphoric acid reacts with sodium hydroxide, and it's up to you to recognize, or I should say it's on you to recognize that whenever you have an acid reacting with a hydroxide, that those two things, that's what makes it a neutralization. All right, Raj, your questions. How does equivalent weight? Equivalent weight. I'm not super familiar with that term. I know what molarity and normality are. So let's take to our useful companion, the internet. Let's see. For acid-base reactions. So it's the mass which supplies 1 mole of hydrogens. All right. So whatever mass of an acid delivers 1 mole of hydrogens is known as the equivalent weight. That's not something that we spent a lot of time talking about. So I won't go over it. I also haven't talked about normality at all. So normality is a concentration unit that will not be on the exam. So molarity, as we know, is moles per liter. So for example, you could have sulfuric acid, and you could have let's say 2.5 molar. All right. Normality is something That is not going to be on the exam. All right. Normality is equal to moles of H plus per liter. All right. So if you had a solution whose molarity was 2.5, the normality would be double, because 1 mole of sulfuric acid has 2 moles of hydrogen, H plus. And so a 2.5 molar solution for H2SO4 would be a 5.0 molar, or sorry, not molar. It's called normal solution. All right. Whereas if you had a different acid, like nitric acid, this would be, let's say this has a molarity. No, I want to make it the same, of a 2.5. Because the ratio of moles, 1 mole of nitric acid only has 1 mole of protons. For nitric acid, a 2.5 molar solution would also be a 2.5 normal solution, because 1 mole of HNO3 has 1 mole of H plus. Now, let me just be explicitly clear. All of this is not on exam 2. So if you did not follow what I was saying, do not worry. You won't be tested on it. All right, another question. Awesome, Sarah. I love that you've got a bunch of questions. I am here to answer them all. Okay, another question. Do we need to know that the density... Oh, interesting question. The equation D equals PMRT. Yes, Faraj, it's just the ratio of the number of moles of hydrogen in 1 mole of that acid. Okay, so Sarah, interesting that you asked about density and gases. So density has an equation. Density is equal to mass over volume, right? And for gases, we have this thing, PV equals nRT. Yeah, so if we do a little bit of algebra, to this situation, so let's focus in on moles for a second. All right. Moles are right there in the ideal gas law. And we know that molecular weight, molar mass, is equal to the mass of a compound divided by moles of said compound, right? And so, let's see. I want to make sure I'm doing this derivation right. Oh, wait, hang on. Sarah, you wrote D equals PM over RT. Sorry, question. Just to make sure. for the... I just want to make sure that I'm actually talking about what you have a question of. You wrote D equals PM over RT. Does D equal density? M equal molecular weight. Okay, sweet. For a second I thought it was molarity. Okay. Yeah. Okay. So let's see. So we know density is equal to mass over volume, right? And we have moles here. If you look at the equation for molecular weight, you have moles in the denominator. If we multiply both sides of the equation for molecular weight by moles, I'm just going to write MW to prevent it from getting mixed up with molarity as I just did. You get an equation that says moles are equal to mass divided by molecular weight. And if we substitute this in here, we get PV is equal to mass over molecular weight times RT. All right. Now, we do a second round of algebraic rearranging and multiply both sides by molecular weight over RTV. All right. Multiply both sides by molecular weight over RTV. You'll see that volume cancels here, RT cancels here, and molecular weight cancels here. What we're left with is an expression that molecular weight times pressure over RT is equal to mass over volume, and this we know is density. So this is an equation that you can derive from the equations for molecular weight, and no worries about the audio delay. We all got there. So this is an equation. This equation that you wrote is an equation we can derive from the ideal gas law, the equation for density, and the equation for molecular weight. Now your question, would you need this equation on the exam? I definitely wouldn't write a problem like this for multiple choice, but I would. There could totally be a question that involves density, maybe molecular weight, and the ideal gas law on the written portion of the exam. So it could totally show up. Would you be unable to solve the problem if you didn't have this expression down here? Not at all. You could totally solve it using the ideal gas law, equation for density, etc. So you wouldn't be out of luck. Could I write a problem that involves it? Totally. Yeah, that's about as committal as I'm willing to go. You should expect to see a lot of unpredictable stuff on the not unpredictable, but different problem types. The multiple choice should feel more or less familiar. The written take home will be a little bit more of a circus, just due to the fact that you'll have 24 hours to do it, access to the internet, your book, and other humans. There will be 3 different versions of the exam going out, all with different problem sets, not just rearranged numbers, but actually different problems. Testing for the same materials, just in different ways. Totally. Other questions? We've been going 101 minutes. I've been having a lot of fun with the streams. So I'm trying to think of filler. Oh, let's see. Okay. Salvage. There's 3 versions of the written test. The multiple choice test. Pretty much everyone's exam is going to be different than everyone else's because of how large I built the problem banks. But you're guaranteed that with 3. I think I said 3, but I think there's going to be 4 versions by the time I'm done. At least 25% of the class will end up with the same version as yours. Okay, Sarah. Also on the subject of gas laws. For the combined gas law, I know that temperature always has to be in Kelvin, but does pressure and volume always have to be in atmospheres or liters? You could totally do torr or milliliters. Yeah. You can totally do torr and or milliliters for the combined gas law. You just have to worry about Kelvin. Yeah, totally. Great question. And the reason why we have to go to Kelvin is because we can't have 0 in a denominator. Also, because Celsius has the possibility of negative temperatures, those would render our answers to be physically meaningless. So we got to watch out for those 2 things. Totally. All right, other questions? Well, let's see. Do you recommend we brush up on nomenclature for the multiple choice? That is a great question. I'm trying to think. I've almost finished. I wouldn't at this point. I've written pretty much all of the multiple choice test bank, and it does not explicitly test for nomenclature. Oh, text test. Yeah, so I would expect to see nomenclature tested for more in the written exam. For example, me giving you the names of reactants or products and you having to write them out and balance a chemical equation. So you'll see that on the written exam for sure, but the multiple choice does not focus on nomenclature. It focuses on material more relevant to the material we've recently covered. So gas laws, thermochemistry, light, and the Rydberg equation. Totally. Let's see. For multiple choice, are every question different from the others, or are some based on others? Okay, so here's how the multiple choice each okay, sorry, I get the question now. Each question is independent. Yeah. Each question is independent. So you don't need to, for example, answer multiple choice question number 2 to be able to answer multiple choice question number 3. Each one is its own self-contained problem. So yeah, so no one problem has any bearing on the other or on another. Great question. Yeah, totally. You'll find that the take-home written exam is complete opposite. Let's see. You said the exam will allow us to flip through the questions, but once we submit, you can't go back. Okay. So the multiple choice exam format is one question at a time. So you can only view one question at a time. But you can, like, if the first one you don't have any idea how to do it, you can skip it, answer problem 2, for example, answer problem 3, go back and answer problem 1. But you are correct, Sarah. Once you submit an answer to a question, you can't try to submit a second answer. So once you submit, it's game over. But if you don't know the answer, you can skip it, do other problems in the exam, and then come back to it. So hopefully that makes sense. Other questions? Totally. I've been grinding on the multiple choice problem bank. And again, this is my first time doing it, so I don't know if I made the problem, if I was too ambitious to make sure that everybody got an individual, unique set of problems by making the bank too large, but it's quite expansive. I'm almost completely done with it. Yeah, I'm 85% full to my target goal of problems for the bank. The multiple choice is available the entire day. Yes, Salvage, that is correct. So the multiple choice will first become available at midnight, 12 a.m. on the 31st, and will close at 11:59 p.m. So you can start the multiple choice exam at any time. Once you start it, you will have 50 minutes to complete the multiple choice exam. There's no way to pause the timer. So time will expire 50 minutes after you begin, but you can start it at any time. If you start it at 11:50, you do need to know that it closes at 11:59. So you would only have 9 minutes to complete it if you start it that late. So don't think you can start right before it closes and get the full time. So be sure to start at least by 11, so you know you'll have the full time to take it. Totally. Out of curiosity, how many questions did I make? A lot. A lot is the answer. I kind of filed it into 10 general conceptual categories that I was testing for based on the material that we're covering in exam 2. And so every student will get 3 questions from each conceptual category drawn at random. Well, you'll be taking 30. Yes, so you'll get 30 because there's 10 conceptual categories. You get 3 from each. But I drew it so that the 3 questions selected, so that the number of combinations for 3 questions selected from the bank for each of the 10, that there would be 56 unique sets for each of the 10 conceptual categories. So each conceptual category is a total of 56 unique problem sets. And then that, combined with the fact that there are 3 sets, is how the total stats were calculated. Oh, right, yeah, Salvage, totally. Yes, but you will individually get 30 questions. But I'm keeping the exact number in the bank hidden underneath my hat. So, Sarah, that's my evasive question to your, out of curiosity, how many questions did I make? Enough to make it take a long time to write and to ensure a unique and fair testing experience for everyone in the class. Again, this is my first time. I don't know if I'm being too thorough or obsessive at this point. But now I'm going to use my new favorite emoji. There's this other YouTube emoji, and I can't tell if the guy's pointing or flipping people off, which makes me afraid to use it in a classroom setting. Because if he's pointing, it could be really useful. If he's but I also don't want to flip off my entire class, because you guys are awesome. I think you totally rock and would never want to flip you off. So I'm afraid to use them. Other questions? I think you're overkilling it, lol. Oh, maybe. Oh, use the flipping off the maybe flipping off YouTube emoji. I don't know. I don't got the guts. I want to be this guy, not this guy. Yeah, but maybe I want to be this guy. Any other questions out there before we conclude the stream? At which point I will disappear into the digital ether and will not reappear until we have class on Wednesday. Let's see, Sarah, it's all like by chance it generates the same exact test for everyone. Yeah, it's because the thing is, in each category problem bank, I make sure that everyone gets the same number of questions testing on the same concepts, and I put all of the questions available in the problem bank at the same difficulty level, and so yeah, there is a chance that 2 people could get the same exam, but I'm just, by building the problem banks as large as I have, it hedges my bet so that that's very, very, very low. And then the chances of those 2 people who defy all the odds, you can see the numbers I crunched. It's like 3 times 10 to the 17th unique exams are possible. And if 2 people got the same one, then you have to think about the chances of those 2 people being 2 humans in the class who actually hang. Because there are some people in the class who don't talk to anyone else in the class. So, yeah, totally. Probably not. I'm going to dab more. Diana, there are no diffusion or effusion problems. Just combined for the gas stuff. Combined ideal and Dalton's. Laws. Oh my gosh. Salvesh, you cracked me up. Oh man. Scientists, everything is finite. Me, Josh, my test questions are infinite. I feel like I might make a pretty cool, like, anime villain, you know? With my infinite questions. My kids and I are still grinding through watching My Hero Academia together. So that's been one of the highlights of quarantine so far. And now I'm just imagining life as an anime, which would be a lot louder, that's for sure, and more colorful. Are there other questions out there? I would make a cool villain for students, eh? Well, that is what I have to say to that. But then you also have the challenge of you get to defeat me. You know, I'm throwing out all of my weird chemistry magic spells at you, but you guys can solve them, beat them, defeat them, cancel them. You know? It's actually kind of exciting. It's kind of exciting. And here's the thing, like, I may be a villain, but I also kind of want you to win. You know, kind of like the Joker actually wants Batman to, like, beat him and catch him because he just loves it so much. I mean, he still kind of wants to win, but he also really, really loves watching Batman do his thing. That's what it's like for me and you. Like, I love writing a test, making it creative, making it challenging, but what I want, it's not to defeat you. I want to see you guys rise victorious, like the Dark Knight. So that's the energy that's going on. We're nemeses that need each other, and actually, I want you to win. Now you know. But I also want to see you earn it. I'm not going to give it to you, just like the Joker won't just give it to Batman. But Batman has many attempts at a Joker. You do too. Salvesh, you totally do too. It's called... No, you do get multiple shots at me, just like the Batman has multiple shots at the Joker. They're called Exam 1, Exam 2, Exam 3, and the final. See, a retake would be like the Joker using the same evil scheme that he used last episode in the next episode. He's never going to do that. It's got to be a different evil scheme every time, right? That's why there's different exams. So you get 4 shots at me to come out victorious. But I change my plan every time. Alrighty. I think in the absence of any more questions, I might go and conclude the stream at this moment in time. Thank you all for watching. There haven't been as many people up in this one. I was anticipating that because this is all exam 3 material. It's another reason why I didn't want to go super deep into fresh material because we'll all need this eventually. But it'll be there for you to rewatch. We'll continue discussing Electron configurations on Wednesday. And yeah, thanks everyone for tuning in. I wish you all the best tomorrow. I am pulling for you, just like the Joker pulls for Batman. Thank you all for coming out. I will catch you on the flip side of this test. I need to go now and finish writing it. Later.